Great. Thanks a lot for coming. Still plenty of people around. So let's get started here. Today, we will only have the recap session. So let me see if this works. So today's recap sessions, I will quickly go through everything that we were doing in the class over the last 14 or 13 weeks. And then in the second part, we'll also go through a tiny exam to show a little bit how everything will look like during the exam session. So let's start at the very, very beginning. What we looked at first was positions. So we looked at position vectors. We looked at different reference frames. So very important, whenever you have a vector, it has to have a reference frame, and that allows you to do calculus with vectors. So that was the point that is introduced here. Then we went into different parameterizations, not because we use them so frequently for the position vectors, but to show you a little bit what parameterizations are and what they mean. We looked into standard Cartesian parameterizations, where the position vector is in essence directly the three entries that we have there, and cylindrical coordinates, where we have these three parameters that allow us to represent a vector. And here we saw for the first time that there's a difference between parameterization and the position. And that became important as a preparation for rotations that we looked in the second part. So here the position vector is obviously a linear function of these three parameters that we have chosen. Then we went into rotations. Rotations are a little more tricky because they're living in SO3. We started with the rotation matrix. I showed you how this rotation matrix is built up. In essence, what we have here in these brackets, these are the axis, the x-axis of the B frame expressed in A frame, the same of the y and of the c-axis. So three column vectors which represent the 3x3 matrix that allows us to rotate a vector which is expressed in B frame using the CAB rotation matrix to the A frame. So this included now 9 parameters in order to describe a rotation. We then looked into different kinds of parameterizations for rotations. We looked into the most standard one that you've certainly seen also in other lectures, Euler angles, where you can also have different arrangements. So here, C, Y, C as a choice. We looked into quaternions, and we showed what is the pros and cons of different types of representations. So here we have 4 parameters. Here we have 3 parameters. We had issues with singularities. We had here unit constraints that we have in there. And then we also did a little bit of an excursion, showing that in particular with quaternions, there is also some algebra that we can do directly within the quaternions. We showed how rotations are related to these operations in quaternions, and how quaternions are then directly related to rotation angles and rotation vectors. So that brought everything together. And last but not least, for all these different choices of parameterizations, we showed that we can essentially just look up these conversions that we once derive, once write down, these conversions between the individual parameters, for example, of the quaternion and the rotation matrix, and obviously also vice versa. So all of that is just a very simple transformation from one to the other. Then after positions rotation, we did time differentiation of that. So we looked at velocities, starting with a linear velocity. So time differentiation of this vector, AB. Also here, a quick excursion about difference between linear velocity and these representations. So G dot and R dot. And we introduced for the first time this E matrix. So this E matrix is the mapping going from time differentiation of parameters to linear velocities, to R dot. And we showed how we can derive these ones. We did this at the example of cylindrical and spherical coordinates. For position space. These are always 3x3 matrices. You can see here. And again, this is something that you write down once and you have it in your library and you just pull it up. If you have to transform from parameterization, time differences of parameterization into velocities. Then we looked at angular velocities, the same thing there. Angular velocity first, so this omega, we showed that this Q symmetric matrix of omega, which is given with this one, this has a direct relationship to time differentiation of rotation matrix and the transpose of the rotation matrix. So once I have the rotation matrix, I can infer what is my omega of that through this. Then looked into the relationship between angular velocities and time differences of time differentiations of representations, and again came up with these transformation matrices in between, these E matrices. In the example of quaternions, that look like this, and we derived it also for the other representations. Now, special here is that we have not a 3x3 matrix anymore, so this is a 4x3 matrix. And like some of the questions that you may see in these ones is that you have to bit understand what are these differences. We maybe give you some examples. You have to see how these things are related to each other, check for dimensions, check for consistency and things like that. So rather on a high level, there will be no questions like directly related to like, pull me out now this matrix. And I don't want to check like who has the best summary of the lecture notes. I expect that you all have that somewhere, but it's more on an understanding level of questions that you're asking here. Then after this, we moved on with kinematics of systems of bodies. We started here with the generalized coordinate description, so these Qs, which represents the numbers of degrees of freedom that we have in our system. We looked at how the end effector position and orientation is a function of this Q. So we have a position, we have an orientation, and we again like use the parameterizations in order to describe this. We can choose here Cartesian coordinates, what we do most often. We can choose here Euler angles or quaternions. And we can now make this relationship between what is my Qs, how does it look like the configuration in joint space, and what is the end effector position and orientation. Yep. Yes. It can be that since we're looking at floating-based systems, and then there is constraints, and these constraints reduce the numbers of degrees of freedom that we have in that specific instant when this constraint is active. So then it's not exactly this. But it can also be that they are not like minimum. If you have a system in the air without additional constraints, then it's the same. Then the number of minimal coordinates and the number of general coordinates is the same. The reason why we quickly discussed about minimal coordinates and the difference is that very often, or like in the classical mechanics, if you're talking about minimal coordinates, you include the constraints in the choice of coordinates. In robotics, you define first a generalized set of coordinates, which is the most generic degrees of freedom that your system can have. And then you have a set of constraints which might be active, which reduce this degree of freedoms that you have in your system. Yes. To give you a simple example, what is this difference? Assume that you would have a floating-based system with a main body that has 6 degrees of freedom. Like once I take this and I nail it to the ground, these 6 degrees of freedom are gone. So I can fully describe in minimal coordinates with only the joint level coordinates. However, the generalized coordinates would include this floating base because we know it can also be in the air and can move around. In here, in this lecture, we really only talk about generalized coordinates. We looked at the relationship between its forward kinematics and its time differentiation. So the forward differential kinematics. First thing is that we did this in a pure analytical way. So if I have a function of Q, and I want to look at how is the deltas in Chi related to the deltas in Q, what I do is a partial differentiation, and I have the deltas here and there. And this was the analytical Jacobian. So the analytical Jacobian is the partial derivative of my end effector, my Chi, with respect to my joint, my Q. So we have Chi dot equals to the analytical Jacobians times Q dot. And we did this also for the geometric Jacobian. What we looked at is what is my end effector velocity, the linear and angular velocity, and how is that related to the Q dots. And in between here, we have this geometric Jacobian. So we had two different Jacobians, an analytic one, which depends on the parameterization, and a geometric one, which is independent of it, which really only relates end effector velocity to joint velocity, vice versa. And again, this matrix that is mapping the J from the analytical space to the geometric space is the same E matrix we've seen before. So I can guarantee you there's going to be some questions about analytical and geometric Jacobians. I also hope that in the meanwhile you understood why we very often use analytical Jacobian in 2D problems, because these ones are the same. These issues really only appear once we go to 3D. So I have here a couple of questions that may come. So one is certainly that we're going to depict you a robot. And for this robot, you have to somehow tell me what are the generalized coordinates. We then talk about maybe dimensionality of the whole problem. And as I said before, like differences between analytical and geometric Jacobians. Now, is this clear? Interrupt me if there's questions. So we know how we get the analytical Jacobian. There we only have to do this partial differentiation. The question was then, how do we get this geometric Jacobian? So what we did look at is at systems of bodies, the kinematic chain of bodies, and we analyzed what is the relationship between end effector velocity and joint space velocity. And we did this simply by propagating through it iteratively to the very end. And what we came up with in the end was that this end effector linear velocity is this matrix here times the joint space velocities. So what we have here is nothing else than the geometric Jacobian. And as you can see, the components of it are some position offset vectors. So these are these offsets that we have, and some directions of rotation axis. So around which axis that this joint is turning. So essentially very simple geometric properties that we can already get from just looking at the robot, and we can directly write down the geometric Jacobian. We did the same thing also for angular velocity. So we looked at how each joint space velocity here contributes to the angular velocity of my end effector. And what we have here as this rotational geometric Jacobian is just all the columns represent the individual n matrices. And again here, remind yourself that these are vectors. These vectors have to have a reference frame. Also, the Jacobian has a reference frame. So if I want to have the Jacobian in world fixed frame, I have to have all these individual vectors in world fixed frame. Same here, right? I do multiply two vectors. I do only multiply vectors if they're expressed in the same reference frame. So that's where all these transformations come into play. So I have to make sure that all of these vectors, they're somehow in the same reference frame, and then I can do the math here. Now in the exam, we're going to look at the chain or a kinematic chain like this. We, as you can see from the experiments or from the exercises we're doing here in the quiz session, but also in the exercise session, this robot cannot be arbitrarily complex, because otherwise you would spend the 2 hours just to do the simple math. We're not going to check whether you can multiply cosine and sine functions. What we will check probably is, for example, we give you certain aspects of these Jacobians. You have to identify other ones. Maybe we give you a Jacobian at a certain point, then we want to know it at another point. Things like this to figure out whether you understood the problem or not. So this was forward differential kinematics. Now we inverted the whole story and we looked at inverse differential kinematics. So we have this relationship between joint space velocities and end effector velocities, which is this geometric Jacobian that we have in between. Now, obviously, what can we do? If you want to figure out what is my Q dot as a function of my W, is I just take the inverse of it. And as we know, this Jacobian, if it's a nicely invertible problem, then we can obviously invert it. But most of the time, we have to take here a pseudo inversion. And then we saw there's different cases. One case is we are getting close to singularity. We may not have enough degrees of freedom in our joints in order to fulfill the end effector velocity. So that meant that we were using a pseudo inversion, or the pseudo inversion was essentially minimizing this error. So figure out what is the Q dot that makes sure that my end effector velocity, the desired one, is tracked as well as possible. I cannot fully track it, but I can track it as well as possible with the numbers of degrees of freedom that I have in my system. The other thing we looked at was redundancy. So if I have too many degrees of freedom in my joints, in order to fulfill a certain task at my end effector, I have multiple solutions that fulfill it. So what we looked at here is how can we now exploit these multiple solutions? If I would take just a pseudo inversion, what that would give me is the Q dot, which is the least square minimal Q dot that makes sure that I'm tracking my end effector desired velocity. So I do this, and then I have my null space projector matrix is N, which is given or a function of my J, which allows me to arbitrarily change my Q dot without violating the task that this is fulfilled. So it allows me now to achieve different motions without changing my end effector motion. And we did this belly dance with that and things like that. So you have the redundancy that you can exploit for this. We looked at different ways in how we can get this null space matrix. And again, very likely, I will not ask you to determine a null space matrix using one of these formulas. Either you can directly see it from looking at the problem, or you tell me what kind of formula you would apply in order to determine this. But what we might ask for is like, what is the expected dimensionality of this null space? What is the rank of it? How many degrees of freedom are left if I solve problem X? What can I do with that? And so on and so forth. So these are the likely problems that we're looking at here. Just to quickly check that I don't forget. Yeah. Then we went towards multitask control. So if you have too many degrees of freedom, obviously I can fulfill multiple tasks. So not only tracking my end effector, but maybe also making sure that my center of gravity remains within a support polygon, my joint moves with a certain velocity, whatever. There's multiple tasks that I can fulfill. And we saw that every task is described by a Jacobian and a desired end effector velocity. And now we came through this whole story of deriving this Jacobian. And the Jacobian itself is just a mapping between joint space velocities to end effector velocities. And end effector velocities in this case is the tasks that we want to fulfill. I want to have a certain end effector velocity. We also looked at different tasks. Imagine that you want to have a task which says elbow joint should have 2 radians per second angular velocity. Then the Jacobian or the matrix here that corresponds to that task is only the selection matrix of this one. So there was a bit of confusion within some of the questions that were asked. So when I talk about tasks, Jacobians are typically geometric mapping functions from joint to task space, from joint to joint space, and be an arbitrary task that I'm defining there. Now, if I have a set of tasks, I can solve them in 2 ways. Option 1 is I give them equal priority. So that means we just stack all the tasks, all the Jacobians, we take the pseudo version, and we stack all the W's on the other side. What does that mean? That means that we are trying to fulfill all these tasks as well as possible, but with equal opportunity, with the equal priority. So we are minimizing the error such that J times Q dot minus this one is minimal. So if I cannot fulfill these tasks, I will equally violate the individual tasks. And then we look at the second approach, is that, well, that might not be the best thing to do. Maybe there's tasks that have a higher priority than other ones. So either I put a weighting function in here, a weighting matrix, that gives more weight to this J1 than to this Jn, but that can lead to numerical problems. You can also, I can also not like absolutely higher prioritize something. I cannot put infinite value for this one and then 0 for that one. So we looked at this multitask prioritization through null space projection. So fulfill task 1, take the null space of it, and make sure that within this null space, you're trying to solve task 2 as well as possible. And again, you're taking the null space of both of these tasks, and you're trying to fulfill task 3 as well as possible without violating the other 2s. And for that, we derived this iterative formula that we can go there. So what you can also expect again for the exam is that we're going to have something like this. I will not expect you to do pseudo inversion of stacked Jacobians and give me numerical values for my Q dot. But I'm expecting that you can tell me what is the difference between these 2s. Maybe you can identify from looking and understanding the problem what is fulfillable and what not, under which constraints, things like that. Questions for this? Was a very important topic that we looked at. Because the same then also came up later when we looked at inverse dynamics. So make a mental note here. We wanted to solve the inverse problem of that. We went through pseudo inversion, which is equal to least square optimization, to this set of tasks, and then we showed how we can use this and solve this with a QP that has different priorities. An exact same problem we encountered later in dynamics. So we had the dynamics equations of motion. We had an inversion problem that we had to somehow fulfill in a least square sense. And we ended up again with like QP problems for that. Then we looked at kinematic control methods. For that, we had to understand what is errors. Now can we embed this in an intrajectory control? So we looked at both positions and rotation errors. A position error is nothing else than my desired position minus my actual position. If I want to have a tracking controller here, I will get my desired from my planner, my feed forward velocity, plus my KP times this error. And I do the mapping from task space to joint space to get my joint space velocity. We did the same thing then also in rotation direction. For that, we had to first understand what is a rotation error. It was a bit tricky. A rotation error doesn't mean that I can take the parameterization of rotation A and the parameterization of rotation B and just subtract them. That is not exactly the error. That's the same as if you would take the Cartesian coordinates of this position and the Cartesian coordinates of this position, and it would make a KP around these Cartesian coordinates. It will lead you on a different trajectory, not on a straight line to this desired point. Same we did for rotations. And what we said here is that this delta is not the subtraction, but what we have to look at is what is the error rotation to rotate frame A to frame B. And I get this rotation matrix. And if I have this rotation matrix, I can then convert it into my delta phi. So the delta phi, essentially, the rotation matrix of it is given by this difference in rotation. And then when we did trajectory control with it, we had again desired omega plus this KP term. And we did the mapping from task space to joint space. Then very briefly, to conclude kinematics, we looked at floating-based systems. So systems that are not rigidly bolted to the ground. What that means is that we have the Q being composed of base coordinates and joint coordinates. And these base coordinates here, these ones, they are composed of a position, this is 3 parameters, and an orientation, this QB rotation, which can be again quaternions, Euler angles, it's your choice. And that gives us a little bit the problematics with this. So Q here, if you look at the dimensionality of that, might be 7, while my actual velocity or my degrees of freedom, again, come back to degrees of freedom, are only 6, right? The free floating body can only have 6 degrees of freedom, 3 for rotation and 3 for position. So again, parameterization is not equal to degrees of freedom that we have there. And also importantly, what we looked at here is kinematic constraints on position level, on velocity level, and on acceleration level. If I'm in contact with the environment, that means the relative velocity of that point that is in contact with the environment or its acceleration, if it remains close, has to be 0. And that gives a constraint on the motion and then also allows us to determine interaction forces. So that's it for the kinematics part. All clear so far? Good. Then the second bigger part of the theory part was about dynamics. And we always looked at these dynamics equations of motion. I think in the meanwhile, you've seen this in plenty examples. And we looked at 3 different methods in how we can get there, how we can determine this mass matrix and Coriolis centrifugal part, gravitational part, external forces, and then the actuation forces. And for all of these methods, what we did, essentially, we started from this principle of virtual work. So a system, a particle, is in dynamic equilibrium if external forces equal to the acceleration times the mass for all the viable virtual displacements that we have. And from that, we then went on. We looked at linear momentum, angular momentum, and the change in this linear and angular momentum. And what we ended up with in the end was the following formula. So the change of linear momentum is equal to these external forces. Change of angular momentum equals to this external torques, as long as we have a free moving body that can move in all directions. So if we had a constrained system, we had to make a free cut to make sure that we can move in all directions, that this equation holds. And then these forces that are given by the joints, they're becoming external forces to the problem. Then we had to get rid of these external forces. So that's the most simple setup. Now, what we did in the second step is, instead of like going through this standard Newton-Euler for individual free floating bodies with the free cut, we said, well, why don't we change this part here? Why don't we make sure that we are formulating this equation only in directions which are feasible given the constraints we're having? And that brought us back to the kinematics, because we know how we can describe the degrees of freedom of our system through Qs. So all feasible motions should be a function of my Qs. So what I have to do is that I have to write down these virtual displacements of every body as a function of Q. So that's what we did with the projected Newton-Euler. So we looked at only the directions which the system can move in the generalized coordinate directions. So essentially we replaced this virtual displacement with Jacobians and virtual displacements in joint space. So we ended up then with this formula here. We have now our delta Qs instead of our deltas in position and rotation. And in here, a number of Jacobians. So what we saw here is that we have mass matrix, Coriolis centrifugal part, and gravitational part. And now this is valid for an arbitrary motion in Q. So we could just set this to 0, and this part has to be 0 here on the right-hand side. To write this down completely, that's how the formula looked like. And what is interesting here to see is what we have in here is few Jacobians, some Jacobians here, we know how we derived them, some masses, some inertia tensors, and that's it. There's not more in these things. One important aspect was that we have to have, again, multiplications of two Jacobians, which we can only do if they're expressed in the same reference frame. So what people most of the time do, just like all the matrices here are in the same reference frame. But you can also have different ones if you want. That's why I wrote here B's and A's. So every block here, whenever I do multiplications, has to be in the same reference frame. Once I do this conversion here, I'm already in this generalized space, so I can have this part done in A frame and that part done in B frame, if I want to. And then finally, we looked at the third method, which is pretty much the same at Lagrange 2, where the equations of motion is a function of this kinetic and potential energy and a couple of partial differentiations with that. I would put the focus on this method for two reasons, or for like maybe one big reason is here, I understand pretty well in how all of these components are built up. So if I add something to my system, I understand how I should manipulate these individual components to complete it. And then the last part of this dynamics was external forces. Now all of that was without external forces, and then we said like now external forces apply to our system. And we looked at how these external forces influence the system dynamics. We looked at this card pole pendulum, can also be an arbitrary other thing, where I have actuators, where I have external forces, and these influence my equations of motion. And I have to understand how do they influence it. So what we looked at is, well, whenever I have an external force, I need to have the Jacobian of that point or body where this external force or torque applies, and use that in order to bring it to my dynamics equations of motion. I did this for a couple of examples. And that's really something that I think could happen in an exam. We know that these equations here, to solve them, A, I know that you can do it, and B, it's just not too interesting to do. But to understand how does a change in my system, an external force, maybe adding another body somewhere, change my dynamics, I think that's something that is absolutely doable in an exam. Yeah.
So which convention are we following for external forces if it's external force acting on the card, we put it on the left-hand side or the right?
Up to you. So you can put it wherever you like it, as long as you have the right sign. So if I have an external force acting on my system, then it has to be on the right-hand side with the positive sign as you draw it in your system. We'll come to that in a second. Here we see it very well. So it's great that you made this point. When we looked at floating-based systems, we had a very important aspect, which was these external forces. And these external forces, when they're acting on our system, and they're on the right-hand side, if it's exerted by the robot to the environment, it's on the left-hand side. Your preference, how you want to do it in the exam. So if we go back to this example that we did the excavator, whether you draw me the force of the environment that acts on your system or the force that your system produces on the environment, I don't care, as long as it's in the right order in your dynamics equations of motion. The other things which were different when we looked at floating-based systems is that we had this selection matrix here. That means not all degrees of freedom are activated. We have this unactivated base. There's no direct force or torque acting on our main body. And in order to balance my main body, the forces and torques that I can apply to it are through my contact points. That is in strong difference to what we looked at later. If you had the quadrature example, there we had only this floating main body. And then the forces that can act on my main body are coming from the thrust. And here it's just coming from the contact. But it's in the end, it's a very similar problem. So we had examples here with these external forces coming from manipulator, legged robots, and UAVs as well. And one more time, and that's more important if you read papers or whatever, people write here Q double dot. It's probably not Q double dot, it's U dot, and U is W, so the omega in rotation direction of the main body. But for convenience, people just write here Q double dot. Then we looked at these external forces that are acting on our system, and that's essentially the big distinction between the different types of machines that we looked at. It can be an external force that is coming from a force model. If you're looking at simulators, you can have spring damper elements on the ground. If you're looking at aerodynamic forces, lifting force, drag forces, that is acting our system. But we also looked at how these external forces can occur due to a constraint. So a constraint says, like, my point is not allowed to move. And to make this point not moving, that's similar if I have a joint, right? If I have a joint, then there's a constraint force that says, like, these 2 points cannot move with respect to these 2 directions. And it's the same here. We have a unilateral constraint that says, like, my point here is not allowed to move. So what I can do is I can take this constraint, and I know this constraint must be valid, and I can then solve from this constraint, given the dynamics equations of motion with this external force, I can solve for the external force. So that tells me if these constraints should be active, you need to apply this amount of external force to the system. And with this, we then showed that we can essentially write down a support consistent dynamics with, again, these null space projector matrices that allow us to project the dynamics equations of motion in subspace where we have no external forces acting in our system. And that became then a little important later when we looked at dynamic controls. Good. Now we have floating dynamics systems. We have an understanding how we write down the dynamics equations of motions for floating-based systems, also if constraints are active. And with this, we went on with dynamic control. Very simple. First control method is let's just look at each joint individually. And what I do now is I make a KP controller, a PD controller for every joint, which means in a physical implementation, it's a spring damper element. So I have my arm here, and I apply a spring damper element to every joint. What it does this. It oscillates a little bit and comes to a configuration, which is not the nominal configuration. Every joint has a little bit of an offset. We said we want to compensate for this in the quasi-static setup. So we added this estimation of the gravity part. And with that, we're able to keep the arm in a nominal configuration. These errors should go to 0. So the errors here of position and velocity will go to 0. Now, there was another problem with that. If I have now a spring damper here, I can compensate for gravity, but I have a spring damper here. The same spring acts now, and it acts now. But I have a very different inertia around this joint. And if you think about the spring and inertia, that gives you a very different dynamics of it. So it can be under oscillate, over damped, whatever. So there can be high oscillations with this. So what you want to have is a compensation for this change of inertia. And this is done through inverse dynamics. In inverse dynamics, all this compensation is done by inverse dynamics, and we are making this PD control on acceleration level. So assume we have a perfect model of our system, then what we could write down with this is essentially joint level PD behavior, where we have just an identity matrix across all the joints. So we can fine tune these PDs and define how the robot should react independent of its current configuration. And then at the very end, we also looked into, because this is also often used in literature, how can we now make combined force and motion control? And we took these selection matrices in here. Now this is coming from, the selection matrices are coming from hard contacts. So assume that I want to do a cleaning. I have no motion in one direction. I have motion in the other direction. That's where the selection is coming from here. If I have a model of my environment that I know for certain motion, there's a certain force applying, I can also have here both a motion and a force at the same time. It was the example that we looked at with the excavator. So the excavator was in the ground, digging. That means it moves, but it has a force at the same time. The soil model gives us this relationship between motion and force. So if I describe the full body dynamics of that, I can understand how the torque has to be shaped such that I produce an end effector force and an end effector motion. Clear? Good. Ugly slide here, but not too much behind it. So what we looked at is now inverse dynamics, but inverse dynamics applied to a floating base system. So remember, this is floating base dynamics. We also showed before that we can now make this projection to get support consistent dynamics. So this equation here has no contact force anymore. Now, if I want to move, I have a desired Q double dot. If I want to move with my desired Q double dot, and I have to identify my torque, all I have to do is I have to now take this thing here, make the pseudo inversion and put it on the left-hand side. So this is what I wrote down here. So the torque is a function of my desired Q double dot, which can be a PD rule on my Qs, on my errors. And again, we have this pseudo inversion in here. What does that mean? If I have a pseudo inversion, that means there must be, or there might be, a null space to it. So this pseudo inversion here has this null space there, which allows us to change the torque without changing this task of how I'm moving. Now, what was that again? If I'm standing and I want to move somehow, I have the motion of the system, that's that part. And now I can change my joint torque distribution without changing the motion. I can change the ground reaction force in between here without changing the motion. All I do is I crank up some muscles that create internal forces within the constraints that I'm applying with my environment. That changes my torque, but doesn't change the way I'm moving. So let me finish this and then we have a break after that. So all of that, bringing all of this together, meant that we always had a task that must be fulfilled. So we have here linear dependency on U's, on forces, on torques. When we looked at the kinematic descriptions, we had linear dependencies between task space velocity, W, joint space velocity, Q dots. So we have always these linear dependencies, and we want to optimize for something. So the most generic way in how we can do this is to understand every point of the optimization as a minimization problem in certain parameters, where all these equations, they are linearly depending on these parameters. So I can stack the parameters that I have as an optimization here, as my optimization variable. And I can write all these equations in this form. I just put the same thing here in these A matrices. So this is equal to A times X minus B. And I can put the same thing for this motion task and the same thing for a force task, whatever. So all these different tasks, I can write as A matrix times X minus B. And I want to make sure that they are equal. If they cannot be equal, they're equal as well as possible. So in a least square sense, that's why we're optimizing this. And if I have more tasks, these additional tasks, they should also be fulfilled as well as possible without violating my higher priorities. So take for every step, I have a null space, and I try to fulfill the next task as well as possible in this null space without violating that task. And that's was the most generic setup or formulation that we came up at the very end. Can be done for inverse dynamics, can be done for inverse kinematics. It's the same. All we change here is my X and then also the A matrices. And with this, we're stopping for the first part and we continue in 10 minutes. Okay, let's continue from here. So this was the last part of the more theoretic part that we looked at. Then in the second half of the whole thing, we went into the different examples. So the 3 domains of quadrupeds first. So what we looked at is like some general elements about quadrupedal system, about actuation, what is important, how you may keep balance or whatever. And then we had a very specific aspect which looked more into the whole modeling aspect. So multi-body dynamics modeling of these quadrupeds, and then the relationship to the controls that we looked at before. So we went through this quiz, and that gives you a little bit of an idea of how I understand how I think what you should understand about these systems from a modeling perspective. And that also relates a little bit to these things here. We will not do null space calculations of A matrices, but I may ask you, what is degrees of freedom of that? If I fulfill that task, is another task still possible? And very often this is, or always, it has to be clear just from an intuitive point of view. I typically, what helps me a lot is if I think about the robot really as a physical system, how can I move it around? What kind of forces can it produce to my environment? Like that, so that I get a proper understanding of the dynamics underneath. Can also be questions about the different types of actuation that we looked into, the quadrupeds and so on and so forth. We did the same thing then also for flying vehicles, first helicopters. Here there was a clear focus on quadrotors. Quadrotors are the most frequently used helicopters that we have in robotics research because they're very dynamic, very agile, easy to control. What we looked at is dynamics equations of motions of this one. And again, like this brings us back to these forces and torques applying in our system. Instead of coming now from external forces through constraints, here these forces are coming through thrust and drag at these individual props. We looked at representing the whole altitude and attitude. Sorry for that. Most often here type Bryan angle, so roll, pitch, yaw of these ones. That was like going back to the first part of the theory that we looked at in the kinematics. And that obviously here connected also nicely to a problem that we're facing in aerial control. When you're going to very extreme maneuvers, that representations like this can lead to deadlocks. We looked at rotation velocities. We showed how we can split this up. So here rotation velocities, angle velocity for roll, pitch, and yaw, how we sum them up with the correspondingly rotated frame. And that ended up in the description of these singularity issues, of these gimbal lock situations. It also showed us in how we can linearize this whole thing. And most of the time with these systems, when you're just flying somewhere, so if you see a drone flying somewhere out there, this is all very linear dynamics. We're not doing very aggressive flights. So we did also look at this in view of controls for it. And the second part of it was related to where do now these forces and moments really come from? So this multi-body dynamics is kind of an over-complex description of this floating vehicle. Because what it is, in essence, is just a single floating body. Mass, inertia, that's it, just one body. We describe this, and then we have all the external forces and moments, which are coming from the gravity acting on our system and from the aerodynamics acting on these systems. Gravity is clear where this comes from, and then for the aerodynamic forces, we looked at thrust forces, and we looked at some of the drag-induced torques. So we have thrust from the 4 props, and then depending on the rotational speed of each prop, they produce different drag forces. If there's imbalance in the velocities in the different directions, you get an imbalance in the drag around the yaw axis, and that on one side allows you to turn it, on the other side is also something that you have to correct. So you do a thrust allocation among these 4 props in order to steer the different degrees of freedom. One important aspect, there's also a long discussion in the Moodle about this, about linearization for control. In terms of aerodynamic forces, we did, it's not an aerodynamics classes, but still like the most important ones for thrust and drag force. We looked at the momentum theory, we looked at the BEM theory, and like came up with very simple principles in how these forces come along. And we did the same thing also for fixed wings. So it was a long introduction about airfoils and how these different airfoils lead you to uplift and drag. So lift force and drag force, which are essentially similar to the thrusters. You have a dependency on velocity square and some parameters to describe the foil and the fluid. And also here, a relatively simplified cascaded control structure with a certain linearization. So these are the two main topics we looked at in quadrotors and fixed wings. And for all these three parts, we also had some insights into what is ongoing research. And that relates also to questions that I was frequently asked. Is this part of the exam or not? So in principle, everything that we're discussing in here is part of the exam. A short answer. A little longer answer. Obviously, we will not ask you about whatever reinforcement learning for quadrupedal systems. What we hoped there was giving you insights into what is exciting research today, that it helped you in getting a better understanding of the topics. We will not ask any detailed questions about these things. Yes. So I can't tell you what exactly you asked because I didn't do the exam yet. But if you would not have attended these things, you should still be able to complete the exam with a 6. Good. I mean, this was really for you. Huh? I will not ask a very detailed question about the controller in this fixed wing system. Yeah. So that brings me to the last important point for you guys. How do we prepare best for the exam? So first of all, it's our goal that you all master the exam. It's not our goal to figure out what is something that you may not know when we try to ask this thing. So the quiz that we were doing here in the lecture and that you have also in the script are certainly a good preparation for it. That shows a little bit what is the level of details that we can ask also with hand calculations. If you want to do more exercises, there is, if you go to this book here that we also uploaded, there is some more exercises that you can do. Obviously, not all of them are relevant, but some of them are pretty interesting. I also strongly encourage you, go to Moodle. There has been more than 60 topics that were discussed. There's another about 100 topics from last year. Go through them, look at what others have been asking. There is some very good insights also in the answers that Mike gave most of the time. I think it helps you, it can help you in getting a better, more in-depth understanding. And again, like not everything that was asked in Moodle is something that we will ask or we will be able to ask also in the exam. Some level of detail there is a lot more detailed than what we would expect. But I think in the end, you all should like collect most possible from this lecture. Then the exam will happen on January 29. It's a Saturday, nice one also for us. What you're allowed to bring is 4 A4 pages of a personal summary. So these are 2 sheets, front and back, or 4 individual sheets, only front page. It's also a very common question. Bring your calculator. We will not have spare calculators with us. No PC. And I don't care what kind of calculator. You can have a tiny one, you can have a programmable one. It will not help you. Then Corona regulations, so like before Corona times, if people still remember, We did in-person Q&A sessions. We have to cancel this, unfortunately. But that means we leave Moodle open, so you can ask all the questions on Moodle. We put here a deadline on the 25th, simply because at the very end, lots of people ask questions, and we want to make sure that we can answer all of these questions. So we'll close midnight 25th. Moodle, you can still access it, you can still read, and you can still learn, but you cannot ask further questions. And we will ensure that like all the questions that you raised will be answered in due time, that you can still use it for the exam. Exam content related to the question before, it's everything that we had in the lectures, but no details from these case studies. Then also questions related to retaking the whole thing in summer, because of, again, this Corona situation. We will offer the same exam, not exactly the same exam, but the exam about this lecture also in summer. No clue when exactly. If you take it not now, and if you take it in summer, the midterms will also count for that exam. If you fail now and you take it in summer, the midterm will also count for that. If you're not doing it now, if you're doing it in summer, if you fail, you can retake it next winter. You can any way take it next winter, but if you take it next winter, you have to re-enroll for the class, which means midterms from this year are out of the game. Either you redo it, redo the midterms, or they will not count. Does that clarify everything related to the exam? Yes, question. So question is if there's a possibility that we change to online exam. I don't know. I don't know what the ETH decides. I have my strongest doubts that we will do it online. So very, very, very likely this will be just an on-site exam. I think they will not manage to change this. If people are not here for a good reason, because you have to start working somewhere, or you're from another university and you have to go back home for lectures there, then you have to contact the examination office and ask for a distance examination. This is typically offered under the constraints that this host university has whatever appropriate supervisors that will give you the exam there, and you have to hand it there with the same constraints as if you would do it here. This doesn't go through us. We will not decide about this. This is all examination office that decides about it. Other questions? Yes.
So what are we expected to know about notations that are used in the exam? So can we expect that it will be consistent from the lecture notes?
We will be at least as consistent as in my lecture notes here and my slides here. I had a couple of typos and mistakes. We try to have no typos and mistakes in the final exam. We try to be as consistent as possible. But I hope you also learned in this class that consistency is not always what you can expect from researchers. Good. Yes.
Does this mean that if we do the exam now in winter and we're not satisfied with it, we can do it again?
So question is, if you're not happy with the grade after this winter session, can you retake it? Answer is no. For all exams, ETH will never allow you, if you pass something, that you can redo it. So you could attend the exam, and then if you realize it's too hard for me, then you hand it in and you fail. I wouldn't do this, honestly. Will not be easier in summer. Yeah. The exams, isn't it online yet? So sorry. The exam typically will happen in Hünkerberg, in one of the drawing rooms in Hill. At least that's where it was like the last 5 years or so. I'm expecting it also to happen there. Good. So I will spend the last 10 minutes just to quickly go through a complete exam with you to take you a little bit of worries about how this will look like. It's going to be structural, content-wise, it's not the same, but structurally it's going to be the same. You have in the first part, we have a couple of yes or no questions. Now here with this multiple choice, it is always true or false. It's not one of them, but there's different ways of how you can make points. If it's true and you cross true, you get 1 point. If it's true and you cross false, you get 0 points. Sorry, if it's true and you cross nothing, you get 0 points. If it's true and you cross false, it's -1 point. Yes. However, the total sum of it will not be negative. Good. So it's 0 or higher than 0. Now, what we want to avoid is random guessing. So tell us if you do not understand what the question asks you, and do not the simple try and error. Most of the time you have already a good estimate of what it could be, and if you know about probability, then you maybe make the risk or take the risk. Yeah, I will hand out this also for you. You don't have to go through it now, but you will see also the type of questions that we're typically asking. So for example, here I give you a quaternion and we ask if this quaternion can correspond to certain rotation or not. Things like this. So all of these ones can be either directly answered, or you need maybe to make a sketch or a one-line explanation for yourself. We do not care about how you came to the solution as long as you don't look it up from your neighbor. Then this was the example with the excavator. We're trying to have every year some different types of robots that we're going through. We're looking at the kinematics of it. So you have to probably give us or tell us what are the individual degrees of freedom, how many queues, what kinds of queues do we need for that. So tell us what is my queue vector. Then here we looked at end effector position and end effector orientation as a function of my queue. It's a planar problem, so it's doable, it's simple. We looked at rotation Jacobian of the end effector. I give you the solution here. This is like the most complex thing. Don't quote me on this, but this is about the most complex thing one can expect. We looked here at Jacobians as well. Yeah, partial differentiation of things like this is probably not the nicest thing to do. So what we did here is I give you the Jacobian of that point, and you tell me the Jacobian of this point. So we had to understand how this difference came along. And then we had questions about inverse kinematics. For example, you move this point now along a certain trajectory. How do I get my q dot? We have the Jacobian. So what we need to do is just a pseudo inversion of it, things like this. Pseudo inversion. And then if I tell you this, right? Now the pseudo inversion of it, then most likely there's going to be questions about, like, is this solution now unique or not? What happens if X or Y is happening, and so on and so forth. Yeah, that was then about the next ones. So if I have multiple tasks that I want to fulfill, and again here, like what happens if I have this null space? I don't expect you to calculate the null space, because also this one is given, right? So we don't expect you to calculate. Maybe in rotation it can be, in a planar problem that's not too tricky. But when you're talking about position Jacobians, not really. Then like continuing like this, but that gives you a bit of an impression of kinematics. Then we went on with dynamics with this. That's actually something we looked at already in the exercise. I don't have to go through this. So given the dynamics equations of motion, so we typically give you parts of it, right? We don't expect you to determine the mass matrix. We tell you this there, and then you can use this. M is now a function of Q, and I can, whenever I write a solution, I can write M, and I know I can determine M from this given function, given my current state, Q. We looked at the controllers of it, so we want to develop now a controller. that produces certain lifting force, certain dragging force, certain motions, and so on and so forth. So these we have seen in the exercises. Yes. Yeah. So we are trying to build up all the exam questions such that either it's a following up mistake that you're doing, but then we're only counting in the first place, and the rest we will involve this in the solution, or we make sure that there's enough difference that it's a reset for your thing. Yeah. What do you mean by the expression? What do you mean by the expression? If I ask you how you would determine M from using projected Newton-Euler given the J's and the small m's, then you would have to write it. But if I give you M here in the equation and tell, look, this M is given, then I don't expect you to write it up. I might expect you to tell me what is this dimensionality of this M. Good. All right, so with this, we're at the end here, a little earlier. So first of all, big thank you for a very active participation. It was a pleasure to have you here. Always very nice discussions, also helping us understanding what the problems are on your side. Most important point here, also take some days off. It's a short time between now and the exam session, but make sure that you take few days off and then with full speed again into the learning. If you're interested in doing more in these things, there's tons of open projects for semester thesis, master thesis, with both of the labs that are involved in this class, so in our group, but also in Sigward's group. Also, if people are interested to either work on this as a researcher, or if one of you thinks the job that Mike was doing was excellent and he wants to do it, or she wants to do it next year as well, then please contact me. I'm always looking also for new TAs for the coming years. That's it. Thanks a lot, and enjoy your holidays. Bye.